Welcome back. We're going to be working on Unit X here today, or at least get started working on Unit X. And you can see that the title of it, I say the foundation of programming is problem solving. And I might even take that a little bit further and say the foundation of everything in information technology is problem solving. And I'm going to say it doesn't matter what field in IT that you're working in. So you could be a networking or cybersecurity person or computer support person or a web person or a software person or a whatever person in IT. And generally what you do as a career is you have some sort of a problem that you or somebody else is having and you're trying to figure out how to solve it. In coding, what we do is we often are given a challenge and it's like, hey, create a program that solves this problem. And then you got to figure out how to do that. Right. And there's a process for it. And this is really kind of an interesting thing. And you can see at the very top of this unit folder, I have kind of like a really kind of brief listing of the topics. Those are sort of reiterated here. And so this is kind of a combination of like showing you the general lay of the land of how units look within these courses. And also understanding these principles, I think is critical to success here. So one of the things that somebody discovered quite a while ago is when you're dealing with logical issues, right? Like a problem, basically, whatever that problem may happen to be, you can solve any problem using these three tools that I have in this bullet list. This is really kind of weird, right? So you can solve a problem by coming up with a series of step-by-step or sequential steps. Or some of those steps might need to be repeated multiple times. Or sometimes when you're trying to solve a problem, you get to the fork in the road, and you either got to go left or you got to go right. So you got to make a selection, right? And using those three techniques, you can solve almost every logical problem. And this all stems from a field of mathematics that's kind of brand new, in terms of historically. And the field of mathematics that I'm talking about is called set theory, right? It was kind of developed in the 1800s. And it's really all about, and maybe you guys remember this from school and hated it, like, like you have like set A, and it's like a circle, and then you have set B, is also circle, and then they kind of overlap, and where they overlap is an intersection, and when you join them together it's a union, and then they exist in a big square, and you call that like the environment. It comes from that, but it's also about probability, and that ties into like quantum mechanics and really really weird little areas like this, like what's possible to happen. And I don't want to go down that rabbit hole, but that's kind of the underpinnings of solving logical problems. Now, I'm going to bring up this slideshow here really quick, and I'm sorry, right? So I apologize in advance whenever I do a PowerPoint, because I would always hate them as a student, and now here I am PowerPointing you guys to death. And I promise not to do this to you often. In fact, it'll be very rare. What's really interesting about this PowerPoint is this was not developed for college students. This was actually developed for students at Lakeview Academy down in Pleasant Prairie, which is a gateway STEM high school. I don't know if you guys are even familiar with it. But our teacher there, Pamela C., many years back, put this PowerPoint together to introduce her like junior or freshman and sophomore students to programming and the concepts. And I thought it was a really nice PowerPoint, so I've borrowed it ever since. It's a little bit dated, but all the principles apply. I am, as you guys can see, I'm not going into slideshow mode. Hate it, by the way. And I'm going to kind of follow through some of this, just so you guys kind of get a general feeling for what these techniques are: sequential, repetition, and selection, with really simple little, examples that hopefully will resonate with you, right? And then this will lead to food, by the way, and we'll talk about that in a second, right? Because I don't know about you guys, but I didn't have dinner and I'm kind of hungry, right? So Let's, I'm singularly minded on food. You know, what's for dinner? All right. So she's got the little tagline here. It's hard, and then suddenly it's easy. And you know, I find this is kind of, we had a really long discussion about this. And by the way, that high school teacher is the one who helped me originally design this Python course when we were launching it. She also helped me choose the textbook because we found that it was good for college level, for advanced college level, and for high school. You know, for people just like, you know, learning the stuff for the first time, because that's really what happens when you're coding. Is it seems like it's like this impossible thing, and then when you kind of see the logic of it, it just all kind of, it's like turning on a color TV after you've been watching black and white, basically. All right, so let's talk about sequence. So sequence essentially means that you're doing things step by step, right? And whenever we do what we call pseudo code, all right, so this is a really interesting word. Pseudo basically means it's kind of like the real thing, code, you know? So it's not really code, it's kind of like code, right? And you'll notice a couple things about pseudocode. Pseudocode often will have a directive, kind of like, okay, go. So there's a start, right? And hey, wait a second, stop, you're done, right? So there's a start and a stop, right? And I'm going to say that normally when you're thinking about step by steps, you're not thinking about the fact that you have to start and stop. But like, if think about getting in a car, if you want to go somewhere, what's the first thing you have to do? Well, you got to start it. And then when you get there, what do you got to do? You got to stop it. That's a really good analogy. I like that one. Right. And basically the way that sequence works is you do this, and then you do that, and then you do that, and then you're done. Right. So what's kind of interesting, you know, and you see like this is the generic format, and down at the bottom, they kind of narrow it down a little bit more. But very often when we're writing computer programs, they fall into this really weird pattern that's built on this thing called systems concepts. So in other words, in a system, we look at things that you feed into the system, something happens to the stuff when you feed it in, and then something comes out. And this analogy extends all the way through IT. And, you know, and Juan, I know you're like an audio guy like me, right? Same thing happens with audio. You got inputs, you do something, you process them, and then you got outputs, right?
That's very true.
Yeah, it is totally true. And it applies to so many different things. So very often in a computer program, when you're interacting with users, you often look for input. So for you might ask the user to click on something or type something in and press enter, right? And then you take that information, and in the background, they usually don't see it, something is processing or calculating. Often it's math, often it's something else, but there's a process going on. And then you get an output, which usually is put something back on the screen. So like you're interacting with the screen, you click something, something happens in the background, you don't know what, and then something happens on the screen as a result, right? Now, if you take that analogy and you apply it to like something like a factory is a system. So a factory might take some logs from the forests up north, cut them all up, mulch them up, turn them into pulp, and then they process those logs, and then out the other end of the factory comes paper. So the input is the log, the process, you know, who knows what happens, but the output is paper. So input, process, output, input, process, output. That's a system. But it's also how most computer programs work. So when we start writing stuff, a lot of it's going to be like this. It's like, what are your inputs? All right. What's your process to solve a problem? And then what's the result of that? Right. So input, processing, output. All right. So now when you start looking at this, like I've already said this, right? We have a start and a stop, right? So pseudocode always technically starts with a start or stop. When we kind of move on, right? You know, and think about this, if it's step by step, you're not supposed to change the steps to solve the problem. So for example, if I'm going to, you know, take an action at home, let's say I'm going to make a pizza, right? Well, step one, take it out of the freezer. Step two, take off the packaging. Step three, preheat the oven. Step 4, put it in the oven, cook it for a certain amount of time. I guess that's 2 steps. Then take it out, cut it up, serve it on plates, and eat it, enjoy it, right? But I can't change that order. I can't like cut it up before. Well, I guess I could cut it up before I cook it, but that probably wouldn't be wise because the cheese would get everywhere. But you guys feel what I'm saying, right? There's a certain step you do it in because that's the way it makes sense, and you can't change that order, right? It's step by step, and it's kind of fixed, right? So, example. First, you put your underwear on, then you put your pants on, and then your shoes. Right. Unless you're wearing shorts, right? Right. Then you can, if your feet aren't too big, you can maybe get your shoes on first. I don't know, whatever. But that's the order, right? That's the order that makes sense. Compare that to a computer program. I might ask for, hey, give me a number. All right, give me another number. Add those 2 numbers together and give me the result. Right. Another example. Right. So then we do like little challenges. I won't make you guys do this, but I'm just going to have you think about it. Like what about if you try to write a program that converts a dog's age to human years, right? And they say like a dog's age, like 7 years for every year that they're alive. So if you have a 10-year-old dog, they're like a 70-year-old, right? I don't know. I've had dogs live much, much longer than that, but that's generally true, especially I think for large dogs. If you could get a large dog to like 10 or 12 years old, I mean, that's pretty good, right? And then you get like a really big breed, like a Great Dane, and they live like 5 years, All right. So how does that work out? Here's how you would do it. First, you got to know what the dog's age is. So you ask for it. You ask your user, hey, what's your dog's age? 10, right? We multiply that by 7, and then we display the results. So that's an example of step-by-step programming. And you can see, not very complicated, but it does follow that formula, and that formula is pervasive, right, in all of programming. Right. So sometimes you have problems where you get to you're solving a problem and you're going step by step, but sometimes some of those steps need to be repeated. Here's an example. If I'm mowing the lawn, right? Step 1, put gas in the mower. Step 2, pull the ripcord, starts. Step 3, wheel it over to the lawn. And then, okay, my lawn's kind of rectangular or whatever. I walk all the way down to the far end and I turn around and come back. Still more grass to cut. Do it again. Just repeat that process until I go all the way back and forth and the whole lawn's cut. Right? So there's a repetition. So while the condition is true, so for example, while the grass is not cut, I keep going back and forth until it's done. Right? And so the repetition can happen with a certain series of steps. So it could be walk one way, walk back, walk one way, walk back, and just keep doing it until the whole lawn is covered. Right? So it's a little series of steps that repeat. That's repetition. Right? And we'll talk about looping, so I don't want you to get your brains too deep into this, but loops often are based upon certain conditions in order for them to operate. The condition I used was like, as long as the grass isn't cut, I'm going to keep cutting, right? All right. So steps go inside those repetitions, right? And when we write code, those steps will be indented. You'll see that. Don't stress on that right now. But here's the challenge, right? So she did this with her high school students. So continue to register Lakeview students until the number of students registered is 410, right? And she's pointing out it's not an if statement. And so basically, we keep registering, and every time we register, we keep track. Well, I got 1 student, 2 students, 3 students, 4 students. I just keep going until I reach 410. Once I reach 410, we're done, right? That's the repetition. All right. The other structure that we talk about, which is selection, sometimes we also call it decision statements. But basically, I think of it as kind of like you have multiple pathways. Which pathway are you choosing, right? So often decision statements in coding, at least the most fundamental kind, are based on if statements. So we say, like, for example, if I have at least 20 bucks in my pocket and I'm hungry, then I can go order a pizza, right? That's how much it costs around here to get a pizza and get it delivered, right? Um, but if I don't have that much, well, then I'm making mac and cheese at home. Right? You see kind of like the example. So we ask a question, and if the condition is true, then we execute the statements, right? And once again, code is indented if it's inside of a statement. All right. So for example, if you were to write pseudocode, so if a person is 18 or older, are they allowed to vote? So it's a question you might ask, right? So if you walked up to like the election place and you show them your ID, but you're 17, they're going to say, sorry, go home, right? Or like these days, are you registered? Right now you have to show your ID these days, which is a thing. All right. So if a person is 18 or older, they can vote. If they're not, they can't. Simple as that. If statements can become much more complicated. So you can have alternate pathways in if statements or decision statements. So in other words, and I'll use the mac and cheese and pizza example again. If I have $20 or more, I can order a pizza. Else, I'm making mac and cheese, because that's what I have at home, or ramen or something like that. And these are decisions. So not both of the statements are going to execute, just the one that applies to the condition of whether it's true or not, right? So this is all of it. Those are the main concepts that I just presented to you, step by step, repeating things or making decisions or selections. Those three things are the fundamental aspects of all programming and all logical problem solving at the same time. There is another tool that you can add on top, which is called recursion, but that's kind of a little bit deeper and harder to explain, at least at this level. Our book does have a chapter on it though, which I think is pretty interesting. And if you're curious, recursion is code that calls itself to execute a problem, right? It's like self-referring code. All right. So the process then of coming up with a solution to a programming problem, we've kind of been doing it already without writing code, is called pseudocoding. And why this is important, right? If I'm going to sit down and write a complicated computer program, I don't just sit down and just start firing off code, right? This is a standard example. If you guys take classes with me, you will hear me say this many times. For example, if I want to build a house, I don't run down to Menards with my pickup truck, load it up with 2x4s, a hammer, and some nails, and get busy. That's not the way. That's not how you build a house, right? I'm not saying it couldn't work, right? Where do you actually start when you want to build a house? You start with a blueprint. Well, a blueprint is basically a solution for how to build a house before you build the house. So you think about all the stuff that you have to do, like what size it is, how tall it is, what materials you're using. And then, if you're a builder that's actually executing that blueprint, what's the sequence of steps you're taking to actually build it? Well, first you got to buy the property, then you got to pour a slab or dig a foundation, you got to pour some concrete, you got to get some footings in there, then you build your framing, and then you choose your siding, and yada yada yada, right? It's a whole process. You don't just buy materials and build. You plan first, you think about it, you sketch it out. You might even get down to the point where you're breaking down all the little steps and everything in minute detail, right? That is exactly what programmers do when they're thinking about a computer problem. If I'm going to write a complicated piece of software, I need to think about, well, what is it going to do? Well, how do I do that? Right. And then what you do is you don't think about building that house all in one fell swoop, like in one weekend. I'm building a house this weekend. Let's go. Right. You think about, well, this weekend, I can paint the windows, or whatever it is. And that's enough of a task. And that's how we write computer programs too. We look at the aspects of the computer program and we think about it in pieces and solve each piece. And then we take all those solved pieces and put them together. And all of a sudden we have a piece of software. And here's a correlation, and Juan, I'm going to pick on you because I know you're like in the music, right? Like I am. This is how musicians think also. People will listen to like a piece of music that I can play and go, how'd you learn all those notes? I'm like, one at a time. you know, or I recognize that this is the verse and that's always like this, and this is the chorus and it's always like that. Another really good example, like I'll do another audio example, like if anybody ever sees like a mixing console, you know, where people like, you know, are mixing audio, they look, there's like 5,000 knobs on the thing. How do you operate that thing? You know, well, they're all little subsets of each other. Well, this one is just like this one. This one just controls that, and this one controls that, and it is in pieces, and it's sequential, and it makes sense. But you break the problem down into pieces, and often professionally, what programmers do is that, you know, if somebody's creating a program like, I don't know, Microsoft Office or one of the products inside of Microsoft Office, it's not one guy coding the whole thing. It's a whole bunch of people working in a bunch of little pieces, right? And the example, if you want to compare it to a house, you know, we bring concrete people in for the foundation. I you know, bring siding people in for the siding, and window people in for the windows, and electrician for the electricity, and plumbers for the plumbing, right? And they're all working on a small piece of the puzzle, and then they stick it together and they got something. It's not that you couldn't do it all yourself, right? But big, complicated things are built that way, right? So this is the mindset. All right. So one of the main tools that we use is pseudocoding, and pseudocoding is basically a set of instructions in plain English that describes what we're going to do with code. So I'm going to do something really super strange here, because I'm going to log into Blackboard, which is our old LMS, not to show you Blackboard, but because I have old courses in here that I want to kind of share with you. And I'm going to try to find, okay, so this is the course I'm looking for. And when, yeah, don't look for answers, by the way, this is an old course. But so when I teach my Java class, I have a final project, and before we build the project, because it's more complicated than your regular weekly homework, we have this like 5-page description of what we're supposed to do, and then we're supposed to convert this into code. And when I first present this to students, like, oh my God, how am I going to do this? Right. So here's where I started. And I did this in the classroom many years ago. Yeah, when we actually were on campus. And so what I did is I used this combination of flow charting and pseudocoding to build me a roadmap of how the application would operate, so that when I sat down to write code, I was just writing individual pieces and then stitching them all together to make the big program. So here's where it started, right? Okay, well, the program's going to fire up. What happens first? Well, it has to pre-create some of the content in the background, right? And then we'll put a menu up on the screen so the user can interact. The user makes a choice. We get their input, and then we check, was that valid input? Yes or no. If it wasn't valid, we put the menu back up. If it was valid, we branch to one of like 3 or 4 or 5 things that were the choices. Each one of those numbers then breaks down to an area. And if it was a survey program, so basically, like if you're taking a survey, how does a survey work? Well, you put the survey up on the screen, you get input from the user, you check if it's valid. Once again, we take note of what the answers were, and then we go back to the main menu, right? And all right, this is not computer code, folks. But if I'm writing computer code, you know, putting a display of question and answers on the screen, well, I know how to code that. Getting the input from the user, I know how to code that. Checking to see if it's valid, I know how to code that, right? So they're all in little pieces. And notice that some stuff is sequential, some stuff loops back, some stuff is a decision point, like this is a decision point, true or false. And then we follow a pathway, and then we write code to match that pathway. So, all right, so this is really kind of a weird way to do it. And I know, well, your heads are probably spinning right now going, oh my God, what did I get myself into, right? I assure you, this is really a great way to learn this stuff when you start thinking about it like this. So here's what I do as a kind of a great first pseudocoding challenge, right? Is I task my students to think about their favorite recipe, right? Not everybody cooks, right? But hey, even, you know, the least, you know, kitchen able of us will like be able to nuke something out of the freezer, right? Or open up a can and heat it up or something like that, right? So I always think of a recipe as a really good example of writing pseudocode. This is really kind of a weird idea. So I'll give you an example, right? So here's what this first assignment is in here. It says, create pseudocode to describe the steps in your favorite meal. Now, first of all, as we look at this, we're looking at a couple of different things. So all the assignments in the course shell here in Python, you can see that I have a format for offering them, right? So like this is how they'll always appear. This is a little legacy from Blackboard, but I always used to put this little assignment flag on there so you could go, oh, that's an assignment, I better do it, right? That's a deliverable, right? So that's kind of my thinking. You will notice that Brightspace also marks it as an assignment, right? The due date is listed. I don't want to change that due date. Sorry, I didn't mean to click on that. And then when I give the description, you'll notice at the very top is the main point of the assignment. What's the point of this assignment? You're going to create pseudocode to describe steps in creating your favorite meal. That's the point. Then there's directions. Think about what your favorite home cooked meal might be, then find a recipe online or from whoever makes this for you, it might be yourself, and then convert the recipe to the verbiage in sequential order, and then create this as a Word document, and then you would submit that document. So I'm going to give you guys an example, right? So I'm going to fire up Microsoft Word. This could be Google Docs or any other, document editor. I'm going to create a new document, and I'm going to go for my favorite recipes here. Actually, I could do waffles, I guess, but I'm going to do my chocolate chip cookie recipe, right? And thank you, Microsoft Word, for automatically fixing my mistypes. And then we'll make that bold and a little bit bigger, and then we'll start listing things. Now, here's kind of an interesting little aspect of this. I could just start writing the instructions like preheat oven, mix ingredients, yada, yada, yada. But there's another really interesting correlation between recipes and computer programming. And this is really a fascinating little aspect. Often when we're creating recipes, we first look at the recipe and look at the list of ingredients. What goes into this, right? So in a computer program, the comparison is what data are we putting into the program? What information or types of information do we need, right? So for example, I might say, 1 egg, 1 cup flour. And by the way, it's probably good to label it and say ingredients, right? And in a computer program, we would call that, data, or we'll talk about that, right? So data fields, whatever. Okay, so 1 egg, 1 cup flour, 1 stick butter, 1/2 cup brown sugar. Notice how Word knows what I'm going to type. 1/2 cup, what would you call it? Regular sugar, 1 teaspoon vanilla, 1 pinch salt, 1 bag semi-sweet chocolate, auto type, there we go, chocolate chips. I'm not sure. Baking powder, I don't know how much, like 1 teaspoon baking powder. I'm just making it up, but that's pretty close to what it is. This would probably actually work as a recipe, right? So those are the ingredients. Okay. So once again, my data feeding into the program. Okay. Then we have the steps. Okay. I guess you could even call it steps, or procedures or whatever. So I'm gonna bold that. Right. Okay, step 1. And the biggest challenge with the steps, right, is when I look at a recipe on a box, like if I pick up a box and look at a recipe for something, they'll often take like 5 steps and put them in one. We'll say preheat oven, pull out your ingredients, blah, 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 and this and that and that, and it's all 1 step. And that's not correct, right? In programming, we can't do that. So step 1 might be preheat oven, to 350 degrees. Step 2, combine dry ingredients in mixing bowl. And you see I'm like struggling to type this, but whatever. Right. And then whatever, whatever your steps are, you're going to detail them. Now, some people have recipes in their head. Like I do a lot of cooking. Like if I make waffles, I don't follow a recipe. I just know, you know what I mean? But if you're baking, that's kind of a different thing, right? It's like little nuances can kind of change stuff. The point is that a recipe is great because it is very step by step, right? And then if you look up a chocolate chip cookie recipe, combine the dry ingredients, mix in the egg, put the butter in there, add the vanilla, whatever your steps are. And then you get to the point where you're putting the stuff on the cookie sheet, right? You got the cookie sheet out. And then what do? You scoop up the batter. I don't know if you guys have ever made chocolate chip cookies, but the way the stuff gets really sticky. So you take 1 spoon, you load up the batter, and then you take a second spoon and use that to drop it on the cookie sheet. And by the way, you should put parchment on that cookie sheet because it's easier to get the cookies off, right? Instead of scraping it. And then, well, all of a sudden, hey, check it out. We're running into a repetition because now I put 1 cookie on the cookie sheet and now I want to fill up that whole cookie sheet. So I keep scooping until when I fill the cookie sheet. So there's a repetition for you, right? So while the cookie sheet is not full, keep scooping cookies, right? And then throw it in the oven, cook it for 15 minutes, pull it out, cool, enjoy with a glass of milk or whatever, But that's the process. So this is kind of what it is. So think about what your favorite recipe may be. And it might be something much more, simple than this. I don't know. But the point is to take a problem, break it down, identify your inputs. You guys seeing like the process here? These are your inputs. The steps are your process, like the actions that you're taking, right? Nobody knows how the cookies are made, but they're sure delicious, right? And then you have an output, which is a cookie. Input, process, output, step by step, feeding in data. What are we getting out? No, we're feeding in ingredients and we're getting out cookies, right? But the strange thing with computer programs is you're often inputting data and you're also extracting data. And actually, I think the more correct way to say it is computer programs often we're inputting raw data and then we're outputting information. Data is different than information. And these are really important topics when you start to think about it in the terms of like the philosophical aspect of what we do as programmers. And I love this stuff, it's like the fruit of life for me, I mean, I think about these things that, we can take a page full of numbers that don't look like anything to anybody, run them through some sort of an algorithm. And there's another keyword for you. An algorithm is a systematic way of solving a problem. And when I come up with a recipe, what I'm really coming up with is the algorithm for solving the creation of the ultimate chocolate chip cookie. And if it's a good algorithm, it works every time. Right. So, I don't know if you guys can feel what I'm saying. So this is an example of how to complete the recipe assignment. All right. What I'm going to do next, though, is, okay, we're going to talk about the software. And I think that maybe we'll actually get to doing that. But there's going to be this problem as well. And we're going to cover this. I don't know if we'll get to it tonight, but I think that it might be kind of like a good one to also work on. And I forget this one's okay. So we're going to work on this one next week. We're going to do some software installation. How do you guys feel about that? Sound good? All right. I'm gonna do
I have
this.
a quick question, Kyle.
Yes, please.
So your ingredients in your process, that's a form of pseudocode.
Yes.
And the same thing as if you were to create a flow chart. Is that
Correct.
another form of pseudocode?
It is. And you know what? and I'm almost trying to avoid walking that path today because I do want to talk about flow charting. But you know
Okay,
what?
that's
Let,
okay. I can wait. I can
no, no,
wait.
no, Phil. You know what? Let's address it because now it's entered the room. You know what I'm saying?
Mhm.
So what Phil's kind of pointing out is there is another way to do this process. And when you looked at that Java programming example that I was giving you before, and you notice how I did kind of a mix of the two. And flowcharting is this weird thing that's been around for a while. And in fact, if you ever study business, this is where I first encountered it, and I hated it when I first thought, this was brought to my attention. I'm like, oh my God, I got to like flowchart stuff. No, that's what my brain said. But then when I learned how to program, I'm like, oh, I see why it's useful. All right, makes sense, right? So you can write things out verbally. That's what pseudocode is. Or what some programmers do is they'll do flowcharts because you can see what it is. So when you do a flowchart, there's shapes that we use. So we show arrows to show the direction of the step. So this step first, usually we go top to bottom or left to right or both, right? So it shows the direction of flow of the process. And then we have different shapes. So a rectangle shape is used for processing steps that happen in the background, like math, right? Or a parallelogram to show that when we're interacting with the user, we're getting information from the user or we're sending information back to them. And then when we're making a decision, we'll have something that we're checking. So is the area greater than 100, whatever that means. And it's either true or false. And depending on which one it is, then it leads to other steps, right? Now, what I'm going to do here is the flow charting piece. I'm going to kind of leave this to next week on purpose, right? And we'll, it is also covered in the videos because I really don't require you to do this very often. It's just an extra credit piece. But I think it's important, since we're on topic with this, that if you guys get a chance, we can talk about this fertilizer problem. You can watch the videos to see it too, but we are going to cover this stuff next week and I will demonstrate how to flow chart. I'll do it really briefly and then I'll show you the solution to this one. Okay. So first thing that I want to do with the software, let's talk about the tools real briefly. I'm looking at the clock going, oh my God, we got 8 minutes left. And I think this is probably wise to record in a separate video. So I'm going to stop this video. So this video ends here.